The theorem is prove that any unital irreducible R module is cyclic. Proof: let M be a unital irreducible R module. Since M is irreducible, so it has two submodules 0 and M itself. If M is equal to 0, then obviously M is cyclic. So if M is not equal to 0, so suppose that M not belongs to M and M not is not equal to 0. Let A is equal to R M naught such that R belongs to capital R. Then we shall prove that A is a submodule of M. Let x comma y belongs to A. Then x is equal to R1 M naught and y is equal to R2 M naught. So x plus y is equal to R1 M naught plus R2 M naught, and it can be written as R1 plus R2 M naught. Since R1 comma R2 belongs to capital R, R1 plus R2 belongs to R, and R1 belongs to R, and minus R1 belongs to R, and x plus y belongs to A, and minus x is equal to minus R1 M naught, or it can be written as minus R1 M naught, and so it can be written as minus x belongs to A. Thus A is a subgroup under addition, and if R belongs to capital R and X belongs to A, so Rx is equal to R1 M naught. R1 M naught belongs to A. Rx belongs to A. So A is a submodule of R. Since M is unital and so 1 belongs to R. 1 dot M naught is equal to M naught, where M naught belongs to M by definition of A. So 1 dot M naught belongs to A is that M naught belongs to A, but M naught is not equal to 0, and so A is not equal to 0. Then A is equal to capital M, since A is a cyclic and so M is also cyclic. Hence, every unital irreducible R module is a cyclic. Now there is a definition. If M is an R module, M1, M2 and so on Ms are submodule of M, then M is said to be direct sum of M1, M2 and so on Ms for every element small m belongs to capital M, can be uniquely expressed as M is equal to M1 plus M2 plus so on plus Ms, where M1 belongs to capital M1 and M2 belongs to capital M2 and so on small m s belongs to capital Ms. Now there is another definition. A R module M is called cyclic if there is M naught is equal to M and small r belongs to R, such that every element of small m belongs to M is of form M is equal to R M naught. And the second definition is N R module M is called irreducible if it has only two submodules 0 and M itself. Again there is a definition. Let M be a R module, then lambda M is equal to X belongs to R such that X M is equal to 0 and M belongs to capital M. Then lambda M is called the 0 M and it is also called left idle of R. Now there is another theorem. An R module M is cyclic if and only if M is equal to R by I, where I is an idle of R. Let M is cyclic and so M is equal to Rx such that X belongs to capital M. We define a mapping phi such that R onto M by phi A is equal to Ax such that X belongs to M. Phi is homomorphism, and then first phi A plus B is equal to A plus B, X is equal to Ax plus Bx is equal to phi A plus phi B, and the second phi AB is equal to ABX, which implies that AX dot BX, which implies that phi A dot phi B. Now phi is onto for every AX belongs to capital M, there is always a unique element A belongs to R such that AX is equal to phi A, and thus phi is onto. If I is kernel phi, then by the fundamental theorem on module homomorphism, we have R by I is equal to M. Conversely, we suppose that M is equal to R by I, then we have to prove that M is cyclic since R by I is generated by 1 plus I, and thus if it is cyclic and M is isomorphic to R by I is equal to, which implies that M is also cyclic.